Hi, my name is Akmal Z, number matrix AN240126. Today, I will explain to you about the chapter 5 of transmission line. So, the communication systems play a vital role in modern society too by enabling the transfer of information over the long distance and uh, high frequency. These systems use various transmission media such as metallic cable, optical fiber, or radio transmission to deliver signals from transmit to the receiver. One of the most important components in communication systems is transmission line. The main purpose of the transmission line is to transmit the signal energy from source to the load with minimal losses. In low-frequency circuits, wire can usually be treated as simple connections. However, in the high frequencies, it cannot be treated. Uh, signal cannot be treated like simple voltage or current. Instead, the transmission medium, play a vital role here. The transmission medium has distributed electrical properties such as the resistance, inductance, and the capacitance, which affect how the signal propagates along the line. If the transmission line is not properly designed or terminated, several problems may occur. These include the signal reflection, the power losses, or the noise interference. Therefore, in this topic, it includes the balanced and unbalanced line, transmission line, characteristics, impedance, velocity factors, standing wave, and also the smooth charge. As we can see here, this is the best option for the transmission, which is the coaxial cable and the two-wire parallel lines. The example for coaxial cable is the Astro wire at our home. Uh, this is because it only consists one cable, and the two wire, uh, as we see the name, it has two conductors. So next slide, I will explain about the balanced and unbalanced transmission line. Okay, I will explain to you about the balanced and also unbalanced transmission line. What's the difference between balanced and the unbalanced transmission line? The balanced transmission lines it consists of two wires, but the unbalanced it only have one conductor. So the balanced transmission line consists two conductor, where one conductor but where both conductor carry current, but one conductor carries signal and one conductor carries as a return. In balanced transmission line, the signal is measured as the voltage difference between the two wires. The current flowing in the two conductors are equal in magnitude but opposite direction. And the advantages for the balanced transmission line is the noise interference, or it called the common mode rejection. The external noise tend to induce the same interference on the both conductors. What does mean by the common mode rejection is if one noise in the single conductor, it will cancel each other. It's called the common mode rejection. So the step by step of the common mode rejection is the first thing first it will interact, and then it will cancel each other, and the noise will end later. So one of the most common example for the balanced transmission line is the two wire coils, two wire, two wire parallel. So the unbalanced transmission lines only one conductor to carry signal, while the other conductor is connected to ground. So the advantages for unbalanced transmission lines is most important things is the low cost and the easy to install. But the disadvantages is the reduced immunity to common mode signal, and the external interference affects the signals more compared to the balanced lines. The common example for the unbalanced transmission line is coaxial cable, which the frequent used in radio frequency or the television system in our daily life. So next slide, I will show the graph of the balanced and the unbalanced transmission. So this one is the balanced transmission line, and this one is the unbalanced transmission line. As you can see, one for the balanced transmission line, one conductor used for the signal and one more used for the as a return path. The common example is the two-wire parallel line. But the unbalanced transmission lines, one conductor uh, carries the signal, but one more goes to return path as the ground. That's all. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal Muhammad Najib. My matrix number is AN240141. Today I will tell you about characteristic and impedance. So characteristic impedance, which is Z0, is the natural resistance in a transmission line. It is measured in ohm, and the Z0 is defined when the transmission line is definitely long or the line is connected to a loop that has the same resistance as Z0. So the transmission line stores the energy because it has an inductance and also capacitance. So as you guys can see, for low frequency we got a formula, high frequency. So for the example, which is he asking about an inductance per meter. So we insert the 75 as a Z0 and 69 picofarad per meter is capacitance, and we got the answer is 0.388 microhenry per meter. And the second answer is if the diameter of the inner conductor is 0.584 millimeter and the dielectric constant of the insulation is 2.23, what is the outer conductor diameter, which is D capital, and we got the answer is 3.77 millimeter. Okay, so for velocity factor, which is we have a formula, and the velocity factor is also known as the velocity constant, and it's defined between the speed at which electromagnetic wave travel through a specific medium and its speed in a vacuum. Okay, so for velocity factor example, the question asks to determine the velocity of propagation and the velocity factor, and which is we have already have a capacitance and dielectric constant and also an inductance, and after that we insert that into a formula and we got the answer, which is 0.66.
Hi, my name is Muhammad Fikrim Nohai Anwar with symmetric number AN240116. So these are the slides for standing wave ratio. A simple definition for standing wave ratio is standing wave ratio, SWR, is also called voltage standing wave ratio. VSWR measures how well a load impedance, Z load, match the characteristic impedance, Z node, of a transmission line. So these are some of the characteristics for standing wave ratio. It's called match line if Z load is equal to Z node, where no reflection and all power absorbed. Secondly, mismatch line, where Z load is not equal to Z node and some part of the wave is reflected. And lastly, incident and reflected wave interfere, forming standing wave with voltage maxima and minima space lambda over 2. So on the right hand side, these are some of the formulas we are usually used to solve a standing wave ratio. First one, we have SWR equals to voltage minimum over voltage maximum. It defines standing wave ratio as ratio of minimum and maximum voltage. Secondly, we are calculating voltage maximum and voltage minimum, where voltage maximum is incident electric field plus reflected electric field, and V minimum is EI minus ER. These are calculating maximum and minimum voltage due to incident and reflected area. The third one, we have a second formula for standing wave ratio, which is the combination of first one and second one is same of calculating SWR based using reflected and incident voltage. For the fourth one, we are calculating a reflection coefficient where ER divided by EI. Find reflection coefficient from the voltage. And the fifth one, we are calculating reflection coefficient where we are using load impedance plus Z naught divided by ZL minus Z load. It determines reflection coefficient from impedance mismatch. And lastly, is impedance load is equal to Z naught, where condition for perfect matching and no reflection where standing wave ratio is equals to 1.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ishak bin Rajasli, numeric AN24013. So today I will continue for the Smith chart part. So the Smith chart is a graphical tool used to analyze transmission line problem involving complex impedance. It helps us determine important parameters such as input impedance and voltage standing wave ratio without lengthening calculation. First, the load impedance is normalized by dividing it by the characteristic impedance. This normalized value is then plotted on the Smith chart. A VSWR circle is drawn through this point, representing all possible impedance along the transmission line. By rotating along the circle, we can find the input impedance at different distance. Moving clockwise means moving toward the generator. Finally, the normalized impedance is converted back to the actual value by multiplying it with the characteristic impedance. This makes the Smith chart a very useful tool in RF and transmission line analysis. Next, we go to the example of the Smith chart. First of all, we need to find the normalized impedance by dividing ZL with the Z0. That we will get 1 plus J3. Next, we can find the VSWR by find the intersection between the middle line of the Smith chart and the circle that we do, that we can find it that is 11. So uh, we can find the lambda of the intersection between the line, a straight line from the center towards the normalized road impedance, that we will find 0.204. After that, we need to add it with the 0.12 that is given from 1.12 lambda. We will get 0.324 lambda, and we need to plot it on the Smith chart, and line uh, we need to line it from the center towards the lambda. We will find the intersection between the circle we did earlier and the straight line. So we will get the Zi, that is 0.45 minus J 1.9. So we will need to multiplying it with the 20, and we get 9 minus J 38. That's all from me. Thank you.